Hey everyone, Dr. D here, and in this video we are covering Chapter 6. So let's get started. Chapter 6 covers metabolism. What is metabolism? Metabolism, you can think about it as all of the chemical reactions happening in an organism. Think about the millions and billions and trillions of chemical reactions going on in your body. That's your metabolism. So metabolism, there's two branches of metabolisms. One of them is called anabolic metabolism. The other branch is called catabolic metabolism. In anabolic metabolism, you're taking small molecules and then assembling them, sort of like how you take, with macromolecules, you take monomers and then you build a polymer. Well, that would be an example of anabolic metabolism, and this requires energy usually. You see, energy is required. In catabolic metabolism, that's the opposite, right? Here you're taking large molecules and you're actually breaking them down, and usually this releases energy, okay? So what is energy? I've been saying the word energy a couple of times. Energy is the capacity to cause change. And here's the thing, that's a very vague, very nondescript, ambiguous definition, but it has to be kind of vague because energy can exist in so many different forms. It's so diverse, right? Anytime you have the capacity to cause change, that is a form of energy. So let's go through some of these forms of energy, and we'll talk about them. So kinetic energy is the energy associated with motion. So if I throw this marker across the room, it's flying across the room, that's motion. If I'm moving about, that's motion. Okay, and I think I have a YouTube video of this, which I'll go ahead and add that, add my little icon here linking that little video I have. I don't know why that icon's not here, but anyway. Kinetic energy is energy of motion. So what's heat? Heat is actually a type of kinetic energy, believe it or not. It's called thermal energy. So here I have my coffee, which I'll take a sip of. Coffee's warm. It's got heat. You know, it's warm. Now, why is that warm? What does that have to do with kinetics? You know, things moving around. Well, the coffee itself is hot because the molecules of water and coffee and whatever, the creamer and all that, those molecules are moving about fast. You can't see them moving, but the molecules themselves are moving quite fast. That's what hot means. When you touch something, it's hot. That means its molecules are moving quickly. You can't see it moving quickly, but on a molecular level, those molecules are moving quickly. So that's why that's movement, right? That's a type of kinetic energy, right? So what's potential energy? Potential energy is the energy that matter possesses because of two reasons, either location or structure. Okay, you got to keep that straight. Either location or structure. Location can give you potential energy. Structure can give you potential energy. So what do I mean by that? Okay, so if I hold this marker up here, it has high potential energy compared to if I put it down there. See, if I put it on the table, it has lower potential energy. If I hold it up above my head, it has higher potential energy. Based on what? Is that based on its location or its structure? That's based on its location, right? Because it's located up here, so it has more energy. See, capacity to cause change. Because look, if I were to let go, there it go. It just converted that potential energy based on its location to kinetic energy. It just converted that type of energy. But if it's on the table, it has less potential energy because it has less potential to cause change or capacity to cause change. If I put it on the floor, it would have even less potential energy because of its location. Now, for the next example, let me go to my garage and get me some magnets. All right, I'll be right back. Break time. Hey everyone, welcome back from break time. So I went to the garage and I picked up some magnets. And what I want to show you is potential energy based on structure. So you know how magnets work, right? They either repel or they attract. Okay, so these magnets are attracted to one another, but what happens if I flip one over? You see they're repelling. They're repelling. But what if I really push them together and really push them together and then you see that structure right there? Yeah, I'm struggling holding the two together. I think one's gonna go flying. But what if I were to let go? You see the structure right now is it has a lot of potential energy in there based on its structure. Whoa, hello. Uh, so it actually flew across my table. But yeah, nothing was destroyed and or damaged, which is good. But did you see that? That structure had a lot of potential energy in it. So that was an example of a structure with high potential energy based on its structure. Now, if I were to hold a magnet up here, you could say it has high potential energy simply because of its location. But if you were to hold a magnet the wrong way around, then you could say it has high potential energy due to its structure. All right, so location versus structure, either way, there's a potential to cause change. Remember, that's what energy means. Energy means causing change, right? So now, what else? Chemical energy. Chemical energy. Uh, Chemical energy is a type of potential energy. What do you think? Are chemicals high potential energy based on the location of the chemical, or do you think it's based on the structure of the chemical? It's based on the structure of the chemical. And we'll explain this. I'll explain this more. You might be wondering, well, how come some chemicals are high energy molecules and some chemicals don't have energy associated with them? You know, what's the difference? And there's a number of reasons why different chemicals have different levels of, chemical energy. A lot of times, it could have to do with charges on the parts of the molecule. It could have to do with how easily it's oxidized, how much energy is released when it's oxidized. So there's a number of reasons why the chemical structure would make it a high chemical energy molecule. We're going to talk about that. But at the end here, look what it says. Energy can be converted from one form to another. Okay, energy can be converted from one form to another. Did you see what I did earlier? I was holding my marker, which has now gone missing. Oh, here it is. I was holding my marker up here, and I said that based on its location, this marker has high potential energy. And then remember what happened when it got released? It then converted the potential energy of its location to kinetic energy, motion, and that in and of itself is a great example of what I'm talking about here at the bottom. You see here it says energy can be converted from one form to another. You can convert energy all day long. Okay, so look at this diver on the platform. This diver would be said to have high potential energy, right? And the diver falls in. Diver converts the potential energy to kinetic energy, and then the diver hits the water, releasing that kinetic energy in a big splash, right? A big impact. Then the diver who's in the water has low potential energy. Does that make sense? Here's another example. This is a hydroelectric dam. So look how high the water level is on this side of the dam, and look how low, you can't even see how low the water level is on the other side of the dam. Okay, so what's going on? You can actually use this to your advantage. You could use the dam not just as a structure, a physical barrier that holds water back. You can also use it for energy. That's why it's called a hydroelectric dam. So what happens is water is higher level on this side and lower level on this side, which means water has higher potential energy on this side. Now, what if you had channels cut into the dam where water flows through those channels and then out the bottom? Well, water would be falling. It would be converting its potential energy to kinetic energy, right? Well, what if you had turbines here? You know, like little turbines, and the water hits the little turbines, spins them, and that generates energy. It generates electricity, and this electricity can be funneled to the town where people can use it to power their homes. Okay, power a small city with the hydroelectric power. So did you see what you did there? You converted potential energy of water to kinetic energy of water to mechanical rotational energy of these turbines to electrical energy, right? Electricity, I should say. Okay, here's an example of another type of energy. This is called octane. Oct is short for, or I should say, another way of saying 8, right? Oct, 8 carbons. Ane means those 8 carbons are all making single bonds between them. Octane, this is what they mean by what they, when you go to the racetrack and they say, high octane action. That means that you've got this octane molecule, this C8H18, I believe it is. Okay, and this octane is burned by the engine of the race car, right? Or by your car. So why is this a high energy molecule? Remember what this is right here? Octane is an example of chemical energy. Why is it a form of chemical energy? So this chemical, octane, must have high energy. Remember what, real quick, let's go back to this. Remember what chemical energy is? A type of potential energy. Potential energy can either be based on location or structure. Which one do you think that is? Which one is octane? Is it based on its location or based on its structure? Well, obviously, structure. The structure of octane makes it a high energy molecule. You know why? Here's why. It's because octane is easily oxidized. And anything that's easily oxidized releases a bunch of energy when oxidized. So what does that mean? Do you guys remember what oxidized means? Remember Leo says grr? These are some notes from before. Let me erase this real quick. Do you guys remember what Leo says grr means? Remember that? I told you that little shortcut. Leo sounds like lion. Lions say grr, right? Grr. Loss of electron means oxidized. Gain of electron means reduced. You guys remember that? Can you see that? Hopefully you can see that. Leo says grr. Loss of electron is oxidized. Gain of electron means reduced. Okay? So, what does oxidized mean? Losing electrons. So, when you have C8, can you see well? I'm trying to see what you see real quick. Yeah, you guys see that. Yeah, that's great. C8H18, right? Plus oxygen. You know, oxygen oxidizes. In fact, do you know where oxidized got its name? Oxidized came from oxygen's ability to steal electrons from things. And it turns out oxygen's quite the little thief, right? It loves to steal electrons from stuff. Because remember, oxygen is way off to the top right of the periodic table of elements. And remember I said electronegativity increases as you go to that top right of the periodic table of elements. And oxygen's one of the greediest electrons there is. I'm sorry, greediest elements there is for electrons, right? Oxygen, super greedy, right? So oxygen steals these H's. It steals those hydrogens because those hydrogens have these yummy electrons in them. Does that make sense? So I mean, this, you don't need to really fully understand this. I'm just explaining this so you get an idea. Octane is a high energy molecule. Why? Because it is easily oxidized. Oxygen steals its electrons. And so what do you get when oxygen reacts with octane? You get the oxygen steals the H's, right? the oxygen steals the H's and becomes H2O, right? And what's left? C's and O's? CO2, right? Now I didn't put the right number of H2O's and the right number of CO2's or the right number of O's, but you get the point. Octane is a high energy molecule because when oxygen's around plus some heat, like a spark from the spark plug, there's this combustion that happens. The hydrogens easily jump over to oxygen. That results in a huge explosion that releases a bunch of energy, and these are the waste products, so you have energy. Energy is released as well. Okay, so octane is a high energy molecule because it is so easily oxidized. It's easily oxidized. Okay, so we've been talking about energy, and I've told you a little bit about how energy can be transferred or transformed, remember, from one type to another, from potential energy, kinetic energy, or remember the hydroelectric dam, how it went from potential energy, kinetic energy, mechanical energy, all this transformation we've been talking about. Well, there's a whole field of science dedicated to studying energy transformations. It's called thermodynamics, okay? Thermodynamics, the study of energy transformations. All right, so we're going to learn a little bit about thermodynamics, but never fear, not anything too in depth. I'll save that for a physics class. So you'll learn all about thermodynamics in physics and in engineering. But in this class, we just need to understand some of the principles of thermodynamics because they do apply to all things in the universe, including biological organisms. So biologists mainly care about organisms, right? We don't care about doing theoretical experiments or thought experiments about what happens inside of a thermos or something, some kind of thermos. Like hold on, I have a thermos right back here. Let me grab it. All right, so here's a nice thermos. This is one of my favorite thermoses. It's metal. I think it's aluminum. It doesn't say, but I believe it's a high-grade aluminum thermos. It's really nice. It keeps my beverages cold or hot, but usually I put cold beverages in here. It's got some water in here. Anyway, if stuff is happening inside of a thermos, if stuff is happening inside of a closed thermos, then the universe, right outside the thermos, the universe can't affect what's happening inside of the thermos, and whatever's happening inside of the thermos cannot affect the universe. You see, that's the definition of a good insulated thermos. All the energy is contained. That would be the ideal perfect thermos, which doesn't really exist, but you get the point. When you're studying thermodynamics, you want to know, are you studying an isolated system, like the liquid in a thermos, or are you studying an open system? An open system where there's energy and matter exchanged between the system and the surroundings. So if we're biologists and we're studying thermodynamics, are organisms an example of an isolated system, like what happens inside of this thermos, where nothing outside the thermos affects it, nothing inside it affects the universe? Or are we more like an open system where, the room, the universe can affect us and we can affect it? What do you think? Obviously, we are open systems. If the room is cold, we get cold. If there's no oxygen, we die. The environment affects you and you affect the environment, right? So organisms are open systems. If a scientist is studying the thermodynamics of humans, they're studying the thermodynamics of an open thermodynamic system. That's just good to understand, okay? So, to understand thermodynamics, you need to know the laws of thermodynamics, okay? And there are 4 main laws of thermodynamics. We're only going to talk about 2 of the laws, the first law and the second law. Those are the 2 laws that we are going to talk about. All right, the first law is that there's no energy created and there's no energy that can be destroyed. Okay, it's called the principle of conservation of energy. You know what this says? The total amount of energy remains constant in the universe. You cannot create energy, you cannot destroy energy, but you can do what? Remember, you can definitely transfer, transform, convert. All of those things are easily done. You can convert energy all day long. You know, right now I'm having this tea time, or sorry, this coffee time. Yep, and I put some milk in there and some sugar. I'm going to be converting that sugar into ATP energy, into kinetic energy, into heat, all day long. No problem, right? Great. So, again, first law of thermodynamics, the total energy of the universe is constant. You cannot create energy, you cannot destroy energy. Energy remains constant in the universe. Now, the second law of thermodynamics is a little trickier. This one's called the law of entropy, okay? The law of entropy. And that is that with every energy, here it says right here, every energy transfer or transformation increases the entropy or disorder, because entropy is a fancy way of saying disorder of the universe. Okay, so let's talk about this. What does entropy mean? Entropy is disorder. And every time energy is transferred or transformed, you have to increase disorder. Okay, so students ask me all the time, like, what does disorder mean? You know, give me an example of disorder. So let me look around my room and find an example to give you. Actually, I have some cards over here. Let me grab these cards. This is a good example. See? Okay. So you see these cards? This is going to probably cause a mess here, but hold on. All right. So I've got these cards, these green cards. All right. You see how I'm putting them in a neat little stack here? They're all ordered. Okay. Okay. All right. So you see, I've got my cards all in a little stack. Would you agree that these are ordered and organized now into one little stack? That's order. Now, if I throw them up, oh man, where'd they even go? Anyway, they kind of went all over the place. You have to take my word for it. I'll have to be hunting those down. Most of them are over there for some reason. Anyway, would you agree that now there's less order and more disorder to those cards wherever they all went? Okay, that's increased disorder right there. I just increased the disorder of the universe. If you have a solid, here's another example. Look, solids are essentially crystals, right? That means that the molecules, why is my coffee hot? Why is my coffee hot? Because the coffee molecules, remember, those molecules are moving around fast. That's why it's hot. Now, what happens when my coffee cools and cools and cools, and I put it in the freezer, it's getting colder and colder? What's happening to the coffee molecules? Oh, guess what? They're moving around. The molecules moving around slower and slower and slower until they pretty much, for the most part, stop moving, right? The coffee itself stops moving. The water in there stops moving. And when it stops moving, that's called frozen. That's a solid, right? That's what a solid means. So solids, look, they're basically the most ordered that matter could be. And then when you heat it up and those molecules start moving, you see that's more disorder because things are moving around. That's going to be more disorder, right? So liquids have more disorder. What about if I heat it up so much it becomes a gas? It starts steaming and evaporating. Well, that gas is just so much disorder. So what you need to know is that in terms of disorder, solids have the least disorder, liquids have more disorder, and gases always have the most disorder. Okay, so disorder. There's many, many different ways of talking about disorder. How about this? Like, let me show you another example of disorder real quick, just so you have an idea of what they mean by disorder. There's so many different ways of talking about disorder. How about this equation? This is the equation for cellular respiration, which we'll learn about later. You don't have to worry about it right now. But C6H12O6, which if you recall is what? That's glucose, right? Glucose or fructose or galactose. Let's just say it's glucose. Glucose plus 6 oxygen, 6O2 becomes what? Cellular respiration says that becomes 6 CO2s and 6 H2Os and some energy, right? ATP energy. We're not going to talk about the energy part, but you see this right here? Okay. All right. So, is there more disorder before the reaction happens or after the reaction happens, do you think? Right? More disorder before the reaction happens or after, right? Think about it, right? Think about it. Like, what if I turn it upside down? No, I'm just kidding. So here's how you could think about it. I could actually tell you that there's more disorder after, right? And why? Simple as this. Look, how many molecules on this side of the equation? There's glucose, that's 1 molecule. And then there's 6 oxygens, that's 6 more molecules. So 6 plus 1 is 7 molecules on this side of the equation, right? 7 molecules. This marker's going bad. I might need another one. How many molecules on the other side of the equation? 6 CO2s plus 6 H2Os give you 12. 12 molecules. So did we increase disorder in this reaction? Yes, we just went from 7 total molecules to 12. That's more disorder. That's more disorder. Anytime you break something down into more pieces, that's more disorder. That's more randomness, right? You know, your room goes from order to disorder, okay? Disorder, all right? So that's what the second law of thermodynamics is really getting at. The entropy of the universe is always increasing. Every time there's energy transfer or transformation, the entropy, the disorder of the universe increases, which is a fascinating thing to think about. You know what that means? Real quick before I move on a little bit, I'm going to tell you about this bear here in this example, but think about this. The universe is more ordered right this second than it will ever be again for the history of time, right? So think about that for a second. Hopefully your mind is blown. But yeah. So let's talk about this bear. Let's talk about this bear. You know what? There's something with the second law of thermodynamics and biology where the second law of thermodynamics and biology come together. There's a paradox. Do you know what a paradox is? I think I looked it up in class the other day, and a paradox is a seemingly absurd contradiction. I think I asked Siri, hey Siri, define paradox.
Paradox means a seemingly absurd or self-contradictory statement or proposition that when investigated or explained may prove to be well-founded or true.
All right, a seemingly absurd or self-contradictory statement or proposition that when investigated or explained may prove to be well-founded or true. Okay, so now you know the definition of a paradox. Let me explain what that has to do with the second law of thermodynamics and biology. Look at this cute little bear. Look at this bear. I mean, he's adorable. He's a bear, right? Look at this bear. And doesn't the bear, you see this nice bear, doesn't the bear have a lot of organization to it, a lot of structure to it? The bear, apparently, look, it has nice fur. It has, it's eating, so it has a digestive system, which includes the stomach, the pancreas, and all the other, organs. It's got intestines and colon and all kinds of enzymes that have to do with its digestive system. It also has a circulatory system. It has a immune system. It has all sorts of things. Nervous system. It has a very complex brain. So this bear is actually highly ordered, highly organized, right? So do you see how that seems to contradict the second law of thermodynamics, like fly in the face of the second law of thermodynamics, which states that the disorder of the universe is only increasing. So basically, if this picture here were, demonstrating the universe, then the universe is only going towards a messy room, right? The universe should only go towards the messy state, the more disordered state. But isn't life like organization? How did the bear come to be in the millions of years of evolution of life on this planet? How did the bear come to be? And I hope you're realizing by this point that the bear, I'm not talking about a bear, I'm talking about life, right? The bear represents life. How did life come to be? If life is so ordered, so organized with these beautiful organ systems and organs, and those organs have these tissues, highly organized, ordered, complex tissues and cells with organelles and these complex macromolecules. It's all very, very ordered, if you ask me. So how did this highly, highly ordered, highly structured bear and life come to be in a universe that's supposedly only going towards disorder and more entropy? Well, does that not appear to be a seemingly absurd, self-contradictory statement? A paradox? Yes, I would say so, but it can be explained. It's a paradox that can be explained. You ready for the explanation? Look at the bear. Here's a bear. He's highly ordered himself, but what is he doing? In this picture, he's getting a free lunch. You see the fish is flying right into its mouth. I'd say this is a good day for this bear. This bear is chowing down on foods, and guess what this bear is getting from the fish? Remember this equation here? Remember this equation here? The bear's getting sugars from the fish. It's also getting fats. Fats are also very organized molecules. And what's the bear do with the sugars and the fats from the fish? Well, it uses oxygen, burns it into CO2 and water. Remember what happens? Is CO2 and water more disorder or sugar, right? Look, the sugar and the oxygen are only 7 molecules, but then the CO2 and the water that produced from that are 12 molecules. So what's the bear doing with these complex sugars and fats? They're breaking them down and releasing them as CO2 and water. So isn't the bear increasing the disorder of the universe? And look what else the bear is doing, moving about, which releases heat. Did you know by definition heat is also disorder? You know why? Because heat is just molecules moving around really, really fast, right? So heat is disorder. You guys need to remember that. Heat is disorder. Breaking down complex molecules into these small CO2s and H2Os, these numerous CO2s and H2Os, that's disorder. So what is the bear in essence? The bear is an entropy machine. You see that? The bear gets to be highly organized and ordered itself because it's causing chaos in the universe, and it's offsetting its entropy. So basically, it's like the universe made a pact with the bear, okay? The universe told the bear, listen, you can be organized and orderly with all your fancy organ systems and whatnot, but you got to pay a tax. You got to pay the entropic penalty, an entropic tax to the universe IRS. Okay, so the bear, in order to be organized, in order to be this creature that lives about on the earth as an organized creature, has to pay an entropic penalty to the universe. It's like, here's my offering. I've eaten sugars and fats. I've broken them down. Here's the disorder. From the moment you're born, you got to eat and drink. You got to break those down. You release heat. You release CO2. You release water. You see what I'm saying? So life does not fly in the face of the second law of thermodynamics because each living creature is a entropy machine, right? And the minute you stop eating and drinking, you run out of energy and you run out of the ability to live and you die, right? You starve to death. That's why you die, because you can no longer pay your entropic penalty to the universe. Anyway, if I haven't blown your mind by now, nothing will. Actually, there are a couple more things that might blow your mind even more about biology. We'll get to them. One of them being, in the chapter 4, which we're going to talk about next, how basically each one of your cells has prokaryotic cells inside called mitochondria. We'll talk about that later. But this is a good stopping point. I think I'll make this a 3-parter series. Chapter 6 will be 3 parts. Okay. One more thing before I go, real quick. Do you know entropy? One thing you need to know about entropy before we go, and we wrap up part 1 of chapter 6 out of 3. One thing you need to know about entropy is this. Entropy means disorder, and the units are big S, all right, capital S. Okay, entropy, the units for entropy are S, big S, means entropy. Entropy, or disorder, okay? So, now you know the 2 laws of thermodynamics. You understand how energy works, okay? We talked about a little bit about thermodynamics, types of energy, difference between anabolic and catabolic metabolism, and metabolism. All right, so that wraps it up for the third, part 1 of 3. All right, thanks for joining me. All right, have a nice day or night or whatever you're watching this video, and tune in next time.